An important neural network architecture in supervised and self-supervised learning is autoencoder. We will discuss key concepts, implementation, and applications of autoencoders. Let us do this simple exercise. Suppose I ask you to draw an image of a 100 monetary unit bill. In this case, I'm using 100 peso bill as an example. You can do the same, for example, on a $100 bill or 100 euro bill. Without looking at the paper bill, draw it from what you can remember. For my case, my drawing is something like this, which is far from the actual 100 peso bill. However, most of the salient features are there, enough for my brain to identify a 100 peso bill. This is the basic concept of autoencoders. Can we extract the minimum set of features needed to perform a task? This has to be done without labels. Autoencoder can be treated as a self-supervised or unsupervised network depending on the intended task. The simplest form of autoencoder simply attempts to reconstruct the given input. This is done by first compressing the input into latent vector using an encoder network. Then the latent vector is used to reconstruct the input using a decoder network. The architecture of an autoencoder is shown here. The input is X. It is compressed into a latent vector H using an encoder. Then the input is reconstructed as X tilde using a decoder. Sometimes the latent vector H is also known as the representation or hidden code. Sometimes the variable Z is used instead of H. In the context of MNIST, an encoder compresses the input digit image into, for example, a 16-dim vector. Then a decoder reconstructs the original image using a decoder. The objective of an autoencoder is not to learn an exact reconstruction of an input image. Instead, it learns only an approximate version of X. In doing so, it is forced to learn only the most important features of the input X. In the paper bill example, our brain stores lossy information about the money, enough to recognize it when we see one. Note that we do not need an exact replica of the paper bill stored in our brain in order to recognize one. In the context of MNIST, the encoder stores information about the writing style, tilt, roundness, thickness, etc. All important properties needed to represent digits 0 to 9. To emphasize, autoencoder is not an identity function. Let us focus on practical applications of autoencoders. First, a decoder can be used as a generative model. Suppose we have a trained autoencoder using a 2-dim latent vector. By encoding an MNIST in 2-dim latent vector, we can project all possible reconstructions on a 2D plot. The X and Y axis are the 2 dimensions of the latent vector. If we observe all possible digits generated anywhere we navigate the latent space, there is always a decodable digit. Some may not be recognizable since some lie at the junction of the transition from one digit to another. In such cases, the decoded digit has properties or features of 2 digits. For example, at the upper right quadrant, we can see a region where the decoded digits may look both 1 and 3. This is an important property and one of the applications of autoencoders. Its decoder can be used as a generative model. It can generate new arbitrary images given random latent vector values. It is like a factory of digits. Second application is the encoder can be used to cluster digits. Again, suppose we train an autoencoder using a 2dim latent vector for ease of interpretation. If we project the latent vectors in 2D space, we can observe that similar digits tend to cluster together. This means we can group them together in clusters. Clustering is one of the applications of unsupervised learning. For example, all zeros tend to cluster in this region bounded by a pink oval. In the future, if there is unknown digit with the encoded vector falling inside this region, it can be classified as 0. That digit has properties or features of a digit 0. The same concept can be extrapolated to other digits in the dataset. There are other applications of autoencoders. For example, it can be used as a compression algorithm similar to JPEG. In the previous example, the sender may have the encoder. The receiver has the decoder. The sender uses the encoder to compress the image into, for example, a 2dim vector. This is much smaller than the 784 dim original image size. Then this 2dim is transmitted over the channel. The receiver decodes the 2dim vector to restore the original image. There are other applications of autoencoders such as feature learning. We will discuss more applications in the succeeding slides. The hidden code seems to contain a lot of information about the input. To be useful, it has dimensionality that is much smaller than the input x. For example, for the MNIST, the x is a 784 tensor. Meanwhile, it could be 2 or 4 for the case of h. With small dimension, the encoder is forced to save only the most important features about the data. How do we train an autoencoder? Similar to other neural networks that we have studied so far, we minimize a loss function. In this case, since we wanted the output to be similar to the input, we can use MSE. Are autoencoders like PCA or principal component analysis? PCA or SBD is limited to learning linear features only. Meanwhile, autoencoders can learn nonlinear feature representations. Autoencoders are more powerful than PCA or SBD. Autoencoders can also be interpreted as stochastic neural networks. The encoder estimates the most probable code for a given input. The decoder estimates the most probable output for a given latent code. The whole network can be trained by minimizing the negative log likelihood. Using graphical model, the encoder, hidden code, and reconstructed output can be represented as shown. There are other practical applications of autoencoders. We can train an autoencoder to remove noise from inputs. We can also train it to add color to grayscale images. Denoising is a problem wherein, given a noisy input, our task is to remove the noise. In this example, the upper 2 rows are noisy MNIST images. The lower 2 rows are MNIST digits with noise removed. An autoencoder can be trained to filter out noise from inputs. Essentially, our reconstructing autoencoder can become a denoising autoencoder by simply changing the input. Instead of feeding the network with clean data and reconstructing it, we feed it with dirty or noise data. Then we force the decoder to recover the clean data. The graphical model of denoising autoencoder is shown here. In this case, we auto-generate noisy data by simply adding noise to the original input data. Then the loss function tries to minimize the distance between the decoded data and the clean data. This essentially trains an autoencoder to be a denoising or dirt-removing neural network. The algorithm for denoising autoencoder, as mentioned, is summarized in this slide. Sample a training sample X from training data. Sample a corrupted version of X using corruption process. Use data points X tilde and X to train the network to estimate autoencoder reconstruction distribution. In this case, H is the latent code. There is a denoising autoencoder in the code example for this discussion. These are additional results showing MNIST with noisy data and the denoise version. Another application of autoencoders is on colorization. Colorization is like the reverse denoising. Given a grayscale image, the neural network adds proper color while keeping the semantics correct. For example, the rice field is green and the sky is blue. It is reverse denoising since we add color or good noise to the input data. This is the graphical model of the colorization autoencoder. It is similar to denoising autoencoder. Given a data set of color images, we remove the color to generate the grayscale images. Then we use the autoencoder to generate the color version. The neural network learns by minimizing the MSE between the synthesized color images and the original version. This is the result of colorization autoencoder on CFAR10 dataset. At the leftmost, we see the ground truth color images. At the middle are the grayscale images. At the rightmost, we can see the colorized grayscale images. We can see that the colorization makes sense. For example, focusing on the lower right images, we can see that the horse is colored brown. The sky above the truck is blue. And the skies above the plane is called white. We will have code demo next. We demonstrate here a simple autoencoder using PyTorch. We separate the encoder from the decoder, and we will fuse them together using the PyTorch lighting module. So essentially, the encoder is trained to encode the input data into latent space. We will use both 16 and 2 latent dim. 16 is good for reconstruction and for purposes of showing how to navigate in the latent space, we will use the 2 dim. We will also use the 16 dim for the denoising autoencoder example. The decoder is trained to reconstruct the input data from the latent space. So this is the first part. We first load all the required modules. Then we build the encoder using PyTorch. The encoder is very simple. It's simply made of 3 convolutional layers as shown here. So at every stage, we double the number of feature maps or filters. At the last stage, we have a linear layer. The purpose of the linear layer is simply to project the feature map, the flattened version of the feature map, into our intended latent vector dimension, or feature dim in this case. After each convolution, we have ReLU activation. Now, this is the decoder. The decoder is also very simple. It's made of 3 convolution layer, but the most important part here is the first linear layer, which is used to resize the latent vector into a square feature map. The reason why we need the square feature map is because we will use a transposed convolution to keep on upsampling the feature map so that at the end, we have restored the original input image size. Note that in order to accomplish the upsampling, we use a stride of equal to 2. After every convolution, we use ReLU activation. Except for the loss, we will use sigmoid. The purpose of the sigmoid is to make sure that all the grayscale pixels are projected between 0 and 1. This is the PyTorch Lightning module, which will fuse the encoder and decoder into an autoencoder. But before we go there, let's discuss first 2 collate FN functions. The first one is the noise collate FN. We will use this for the denoising autoencoder. Essentially, here we will sample batch of images, and for each batch, we will introduce noise. So it will generate noise version, which is XN in this case, and the clean version. So essentially, we return both the noise and the clean version. Meanwhile, for the reconstructing autoencoder, this is our collate function, which will simply return 2 sets. Both are clean data, identical. Now, this is the autoencoder. And we will use here a loss function, which is MSE. And the forward function of the autoencoder is shown here. We will first encode it into H, and then the X tilde is reconstructed using a decoder. And this is the usual training step, the test step. And for the optimizer, we use the Adam with learning rate of 0.001, and we use cosine annealing learning rate scheduler. This is the train data loader, which we already built into the PyTorch Lightning module. This will simply load the MNIST data, both for train and test. And depending whether we want denoising or reconstructing, we will load the corresponding collate FN function. Now, then this is the argument, and this is similar to all our previous example. The one that's different here is the feature dim, which you can modify, and whether you want denoising or not. For the reconstructing, we use 16 dim so that we have more faithful reproduction. For the feature dim, because we want to show how a decoder can be used as a generative model, we will just use a 2 dim. Okay, that's for simplicity and ease of interpretation. And this is the usual callback using weights and biases so that we can visualize the reconstruction, the denoising as well. So we train using the trainer, and this is the 1B logger. Now, Suppose we use the 2dim latent vector. Okay, we have already trained, okay, and we want to use the decoder as a generative model. This can be shown here at the end. So this is the decoder of our autoencoder. What we're going to do is we will generate random numbers using normal distribution. Now, that number or those numbers will be used in the latent vector, which we will then inject to the decoder, and let's see whether the decoder can generate random digits, MNIST digits. Okay, so this is the first one. It looks like 5, and if you keep on pressing this, keep on sampling, you will generate different MNIST digits as shown here. This is 8. This doesn't look like it. Maybe 3, and this may be 2. This is 6. This may be 3. This may be 2. This may be a little bit 3 or 1. This is 3. This is 5. This is maybe 1. This is 3. That's 0. And that's 5 and 3 and so forth. Now let's take a look at the output on our 1B side. So this is the result on 1B. Here we have, this is the input image, and this is the reconstructed image. In this case, I'm using 6dim for my autoencoder. And you can see here that the reconstruction is very good. Now let's move on to denoising autoencoder. This is our denoising autoencoder. And from what you can see here, these are the noisy input images, and these are the clean version. So the performance is really good. For example, you can see here, you can barely see the number 4 here, or the digit 4, but you can see clearly the digit 4 here. Here is the digit 9, and you can see clearly here the digit 9. This is digit 5, and you can see the denoised version, digit 5. This is the colorization autoencoder, and this is pretty much the same as the previous example on denoising and reconstruction autoencoder. The main difference, however, is we will use CFAR10 dataset because we need color images. This is the encoder part, and here the main difference, however, is we will use a feature thing on 256 because the task of colorization is much more difficult compared to the denoising, for example. And we also increase the number of filters here to 64. That's the initial number of filters. Now, for the decoder, we made it to 4 convolutional layers because, again, adding or figuring out the color is much more difficult. We use the same feature dim, which is 256. And we also increase the number of filters. The last layer will generate 3 output channels because we need RGB, and we also still using sigmoid for the last activation. This is different for the Lightning module autoencoder. In this case, we introduce gray collate FN, which will simply convert RGB images to grayscale images. We will use that in our data loader. So the data loader will simply generate grayscale and its corresponding color version. So everything the same, even the optimizer and the learning rate scheduler. So after training this, we can head on to the 1B site to visualize the output of the colorization. This is the additional difference. Of course, the training data loader and the test data loader will use CFAR10. The arguments and the callback for visualization later. And this is the actual training using the trainer of PyTorch Lightning. Let's head on to 1B side to visualize the outputs. So this is the weights and biases visualization. And in this case, let's take a look. These are the ground truth color images. This is the grayscale version, and these are the colorized images using the Colorization Autoencoder. For example, take a look at this one. The sky is blue. It's able to, this is a plane, and above the plane is the sky. And this is, I believe this is a cat. This is a cat grayscale, and here we were able to colorize the cat pretty much very well. Okay. And this is a horse. This is a grayscale version of that horse, and this is the colorized horse. This is a ship, and the sea here is colored green, but here the autoencoder says, you know, maybe the sea should be blue. That's it. Thank you.